All right, today we are going to be still solving systems of equations, but we're going to look at some special cases. So far this chapter, every time we solved a system of equations, we've always gotten one solution. So in fact, all of our problems have looked like this. When we graphed the two equations, we got one solution, which was an ordered pair, xy, and we learned how we could check it by plugging the x and y values back into the original equations to check them, and so forth. So every problem we've done so far, we have gotten an answer, an ordered pair answer. Well, when you graph two equations, two linear equations, that's not the only possibility that you can get. You could graph the two equations and they could be parallel lines, like our second example here. And if our solution, remember our solution represents, it's a common solution to both equations. But in this case, if the lines are parallel, there is no intersection. There is no common solution to the two equations. And that's why it's no solution. There is no point in common that is on both lines. Notice when we have parallel lines, the slant of the line is the slope. So if the lines are parallel, they have the same slope right there. So, and also notice they have the same slope, but here on our graph, they would have different y-intercepts. The other possibility, and I know it sounds really strange, is you go to graph the two equations and they are the same equation. They might not look like it at first, but when you put them in y equals mx plus b form or slope-intercept form, they end up being the same equation. So when you go to graph the two lines, they're the same line, which means you have infinitely many solutions. Every single point on this line is a common solution to both of them because they're the same. And so the lines are the same. They have the same slope, same y-intercept. Everything's the same. So if that happens, you have infinitely many solutions. Well, we can definitely see these relationships if we graph them. So let's look at this example and graph the two equations. This first one here, we need to fix that up. So I'm going to do 2x minus y equals 5. Let's put it in slope-intercept form. So here we go. And dividing everything by -1, we get y equals 2x minus 5. So we have y equals 2x minus 5, y equals 2x plus 1. Now, you might be thinking already, looking at those two slopes and y-intercepts, you know what's going to happen. Well, let's see. Let's graph the two of them. So here we are at +1. I'm graphing this one first. Up 2 over 1, up 2 over 1, up 2 over 1, and so forth to graph the best line that we can here. And that is the first one, so that's purple. I'm going to graph the other line. I'm going to graph this one in green. Here we are at -5, up 2 over 1, up 2 over 1, and so forth. And we're going to connect those points. And hopefully this is what you were supposing. The lines are parallel, which means we have no solution. Notice that for this first equation, our slope was 2 and our y-intercept is 1. For this one, our slope is 2, our y-intercept is -5. So we could see we had the same slope, different y-intercepts. So if you have just the two equations in slope-intercept form, you could determine that if they have the same slope with different y-intercepts, it would be no solution. But what if we approach the problem a different way? I'll just draw a line here. What if we took our original two equations, 2x minus y equals 5 and y equals 2x plus 1, and instead of graphing it or putting them in slope-intercept form, let's say you said, oh, this looks like substitution. And you took this and plugged it in for y into the first equation. Well, let's see what happens if we would have approached this problem with substitution. Well, let's distribute. Okay. Oh, why did I write 1? That should be a 5. I knew something was weird. Notice these 2x minus 2x cancels out, and we're left with -1 equals 5. Well, that is false. That is not true. And if you remember back in first semester, whenever we had a situation where all the variables canceled out and we had something that was false, it was no solution, right? It was no solution because it never can be true, and anytime something is false, that is no solution. So no matter how you approach these problems, and you can see there's many ways of doing it, whether you put them in slope-intercept form and look at the slopes and y-intercepts, or you try to solve it by substitution or elimination, we come up with the same answer, no solution. Let's look at one more problem. These two equations right here are kind of set up for elimination, and we'll look at that in a minute. But first, let's graph them. So I'm going to take this first equation, -2x plus y equals 3, and I'm going to put it in slope-intercept form. Looks like we get y equals 2x plus 3. Now I'm going to do my other one in a different color. So this is -4x plus 2y equals 6. Let's do this and divide everything by 2. Y equals 2x plus 3. Will you look at that? They didn't look the same when we started, but when we put them in slope-intercept form, they're the same equation. So if we went to graph this, we would start at 3 up to over 1. How about that same 2 slope? But it's the same equation. We would only do one line. That's it. So it's also the blue line. I'm just going to do it both. To show you, pink and blue, it's the same line, which means infinite solutions, right? Infinite solutions. Well, just like last time, what if instead of graphing and putting them in slope-intercept form, we try to solve it by elimination? So let me put my two equations here. And if we were going to solve this, if we were going to solve this by elimination, we would multiply this first equation by -2 so that we get 4x minus 2y equals -6. And then recopying my second equation, I get that. Now, when I add them together, those cancel out, those cancel out, those cancel out. It's not a no solution, but if there's nothing left on the left side, it's 0. If there's nothing left on the right side, it's 0. So 0 equals 0 is true. And when we get something where all the variables cancel out, and it's something like 5 equals 5 or 0 equals 0 in this case, that means it's always true. And so that does mean infinite solutions. So you can see there's many ways to look at these problems. And so if you approach a problem by substitution or elimination and something unusual happens, which many will happen in this section, that's what it means. That there are the possibilities of no solutions and infinite solutions. Good luck.